Hi. So this is a model of grid connected PV system with the partial shading effect. So here I'm going to create a partial shading concept by making two parallel string, right? So here you can see that. So this is one string. So this is another string. So both are connected in parallel. So there are two parallel string, and then the total power rating, right? The total power rating is 3 megawatt. So that means each string going to be supply 1.5 megawatt. Okay, both are connected in parallel. So totally we are getting 3 megawatt. And the single string is connected. That means the each string having three group of array. Okay, so each group of array, that means the first group having 650 parallel string and four series connected model, and then second group having 650 parallel string and then four series connected model, and then here we are getting 650 parallel string and three series connected model. Okay, so totally you can see here, right? So total the voltage will be 4 plus 4 plus 3 into the single PV array voltage, so 29. Okay, so that means the voltage across in the first parallel string, this one, right? So which is equal to, so 4 plus 4 plus 3, so 11, so 11 into 29. Okay, so it's around 319. So voltage will be 319. Okay, so that voltage at that means at the standard test condition like 1000 watts per meter square and 25 degrees Celsius, right? So voltage in the PV terminal when we are applying MPPT, so we are getting around 319 volt. Okay, so both are connected in parallel, so both voltage will be same during at the standard test condition. Okay, and then so here we are using boost converter. The boost converter used for boosting the voltage from 319 to 700 volt. So here we have 700 volt. Okay, so here I'm going to take the 700 volt because it is going to be connected to 400 volt line to line three phase grid. Okay, so that's why I'm fixing 400 volt. Okay, so this L and C value going to be calculated based upon the input voltage 319 and output voltage, and then total power rating of this PV panel. So total power rating already told, right, around 3 megawatt it going to be generate. So based upon that detail, so here we are calculating L and C value. So here you can see here, right, the power of the PV is around 3.048 megawatt, and then input voltage from that PV 11 into 29, and then switching frequency is 10 kilohertz, and then output voltage of the boost converter is 700 volt. So from that we have to calculate IOT max. So this is for calculating ripple inductor current. So this is used for calculating a ripple volt capacitor voltage. So based upon this detail, right, we are going to calculate L and C, and then here we are calculating duty cycle and load resistance. Okay, so once we execute this M5, we can see here this is the value of boost converter inductor and boost converter capacitor, and then this is a operating frequency at the standard test condition. Okay, duty cycle. Okay, so that value is placed here, right, and then the input capacitance also we will take the same capacitance value. Okay, and then here you can see that the each PV group, right, going to be connected with the temperature and irradiation. So here I am creating that the change in irradiation and detail, that for creating partial shading effect. So after 1 second it will change to 1000 to 800, and then here we change to 1000 to 600, and here we are changing 1000 to 500 after 1 second. So here you can see that the same kind of variation we are providing, right? That means initially all PV panel will be operated at standard irradiation condition. That means it will be operated to 1000 watts per meter square. After 1 second, right, the first two will be operated at 800, and this two will be operated to 600, and this two will be operated to 500. So in order to create that partial shading effect. Okay, and this boost converter, right? So this boost converter going to be controlled by means of MPPT algorithm. So for that we need two input, one is PV voltage and current. So here we are measuring the PV voltage, and here we are measuring the PV current. So that going to be processed via MPPT algorithm. So inside MPPT algorithm we are using, that means here we are using the P and O MPPT. Okay, so here we need to provide, here we are measuring the voltage and current of PV panel, and here we are fixing the 4 parameter. So one is initial duty cycle. Here initial duty cycle I am fixing is 0.42, and maximum duty cycle we are fixing 0.9. The minimum duty cycle we are fixing 0.1, and then change in duty cycle we are fixing here is 0.08. And then so in order to execute P and O MPPT, so we need to fix 3 more. That means we have to initialize 3 more parameter. So that is nothing but the previous instant voltage, power, and duty cycle. So initially these 3 parameter, these 3 variable does not have any values. Okay, so we are going to check the value whether it is having value or not. If it is empty, then you have to provide value for V volt, P volt, and the D reference volt will be taken as a initial duty cycle. So next here we are calculating the power of the PV, and then here we are calculating the del V and del P, just comparing the current instant voltage with the previous instant voltage, and current instant power with the previous instant power. Okay, so here the V and P nothing but the current instant voltage and power. So after that, next you have to check del P. If del P is greater than 0, next you have to check del V. Okay, if del V is greater than 0, we need to decrement the duty cycle in order to extract the maximum power from the PV panel. If the del V is not greater than 0, next you have to increment the duty cycle to extract the maximum power from the PV, and then you have to check the del P. Okay, if del P is less than 0, again you have to check del V. Okay, if del V is greater than 0, you have to increment, or del V is less than 0, you have to decrement. That means you are taking the opposite to that these conditions, these two conditions. Okay, if suppose if del B equal to 0, just you have to maintain the D reference, duty cycle reference will be the previous instant duty cycle. Okay, so after calculating this D reference, okay, so you have to compare the D reference is within that maximum minimum limit. Okay, so that's why here we are checking with the limit of D reference whether it is in between maximum to minimum value. If it is that means if any one condition is not satisfied, okay, then we have to maintain the previous, that means the duty cycle reference will be previous duty cycle. So here we are overwriting the current duty cycle, current power, and current voltage with the previous duty cycle, previous power, and previous voltage. Okay, so this code will be keep on executing to extract the maximum power from the PV panel. So here we are getting that duty cycle. That duty cycle is going to be processed by this pendulum generator. So this pendulum generator going to be generate the pulse. Okay, and then it will be control this IGBT in order to extract the maximum power from the PV, as well as boost the voltage from 319 to 700. Okay, so next to process we are connecting this, the output of boost converter, right? The output of boost converter will be connected to the grid via this voltage source, inverter, and then filter inductor. Okay, so we need to design this filter inductor. So filter inductor design based upon the power rating of the PV, and then the voltage across this inverter, and then line to line voltage, frequency of operation. Okay, so for that we have the equation. Here you have the apparent power going to be taken as the PV power at the standard test condition. So 3048, otherwise called 3.048 megawatt, and VDC is 700 volt, and VAC, that means line to line voltage, is 400. So this is the ripple inductor current in the filter inductor, and then this is modulation index. So this is switching frequency, and this is the calculation for that filter inductor. Okay, so once you have to execute this file, you will get the inductance, filter inductor in the grid side. Okay, so here you can see that this is a filter inductor. So you have to place the filter inductor value in this inductor. Okay, so next process, you need to control this inverter not to take the power from the PV, and then you should be inject to the grid. Okay, so for that, here we need to measure the VDC. Okay, so here we have to filter out that this boost converter voltage, so by means of low pass filter, and then you have to measure this one, and then this going to be compared with the 700 volt, because we need to maintain 700 volt across this inverter. So we have to compare with 700, and then it's going to be converted into per unit, right? So here you need to maintain it 700, so that's why you have to divide with the 700 to converting the to per unit, and then it's going to be processed via PA controller. Okay, so this PA controller can be tuned by means of PID tuner. So or else you can use the trial and error method. So here we are using trial and error method. So first I'm going to apply the small value for this KP, KA. Okay, and then I'm going to check the result of the grid volt, and that means PV voltage, PV current, PV power, and also I'm going to check the result of grid side, right? Grid voltage, grid current, everything. Okay, so based upon the things you have to adjust the KPK value. Later I will explain. So this will be considered as ID reference, and here we are measuring the grid current. Okay, so here we are measuring grid current. The grid current will be converted into per unit. Okay, per unit, and then it will be converted into DQ form. So by using ABC to DQ naught transformation. Okay, so for that we need omega t. So omega t is calculated based upon the grid voltage. So you have to take grid voltage and then process via 3-phase PLL, and then it will be provide the omega t. So omega t nothing but phase angle with respect to time. Okay, and then you have to use only ID and IQ, right? After conversion of IG in the form from ABC to DQ naught, then you have to take only DQ. Okay, DQ value. Okay, and then it will be compared with the reference DQ. Again it will be processed via PI controller. So this PI controller will be generated the control signal. So here PI controller I am going to take only the KPKA equal to 1 default value. I didn't change anything here. I kept it as it is 1, and then finally after processing via PA controller, we are getting the control signal, and then control signal when we pass, that may convert it into ABC by inverse spark transformation. So this is inverse spark transformation. Okay, after that we are having controlled voltage in the form of ABC. So here we are processing via the 2-level PWM generator, and then it will be generate the pulse for this inverter. Okay, so in order to get the proper output, so you need to tune this KP and KA value of this voltage controller. So initially you have to put 1 and then check the result, and then slightly you have to increase the KP and KA value for getting the better results. Okay, so for value of KP equal to 5 and KA equal to 5, I am getting the better results. So it will take some time to get the proper results, or else you can use tune up, right? So here, so this control will be control the inverter according with the that mean the DC link voltage as well as current control, right? Grid current control. And then here you are using rate limiter, right? So why I am using rate limiter means, and that means I am going to limit the irradiation. That means sudden change in irradiation. That means normally when you are going to use step input, right? So it will be suddenly decrease or it will be suddenly increase, right? So when you have to use the directly, what will be happen, right? Due to some problem, you will get some error, right? That means simulation ill defined function error. So in order to avoid that problem, so here we are using rate limiter. So rate limiter nothing but it will be limit the, yeah, that means response, right? If suppose the irradiation will be changed suddenly, we are giving command suddenly, right? So what will happen, it will be changed like this. So it will be converted into like ramp changing input, right? So it will be take some time to achieve that the final value. Okay, so when you have to use this kind of waveform, then you will not get any error in the system. So for that purpose only we are using rate limiter. So when you are using the rate limiter around 10,000 or minus 10,000, so what will be happen, right? So the response will be very quick, right? Otherwise suppose you are using the rate limiter is very low, right? So then what will be happen, it will be take a long time to settle the irradiation. So it will take long time to settle to that final irradiation value. So you must use a high value. So better you can use the 10,000 slew rate, right? Slew rate nothing but is kind of um, like slope, right? We are using slope or rising, right? So here I am using 10,000 slew rate. So then it will be changed quickly, and then you will not get any error in the system. Okay, so that's why we are using this rate limiter. And then I'm going to simulate this model and then explain the results. Now you can see the model is running. So I'm going to open the PV detail and then grid detail and power detail. Okay, so here you can see that now that voltage is maintained around 320 volt, and then current is maintained around 9,000 amps, right? And then here you can see that PV power is around 3 megawatt. So now the all panel, right, will be operated 1000 watts per meter square. Okay, so after 1 second what will happen, the irradiation will be changed uh, to 1000 to 800, and then 1000 to 600 and 1000 to 500, and then you will see that result. Okay, so here you can see that. So this is a grid voltage, grid current. So this is inverter voltage and inverter current, and then this is a grid and inverter power. Okay, whatever power we are generating, that power is generating from the PV is going to be given to grid. Okay, So now you can see here, right? The irradiation will be changed to 1800 and 600, 500. So because of that, you can see that, right? The there will be a small change in voltage, and then the current will be decreased. Okay, and then power comes to 2 megawatt, right? So for different irradiation partial shading condition, the PV is extracting the maximum power from the PV panel. Okay, and also you can see a rate reduction in the grid current and the inverter current. Also here also you can see that there is reduction in the grid power and the inverter power. So let me change the detail again. So I'm going to make, so this will equal to 500, and this is going to 500, and this is going to 500, and this is also I'm going to make 500, and this is also I'm going to make 500. So now we can see the result. So because of change in the condition, you can see that all model irradiation changed to 500, and then here you can see that we are getting around 1.5 megawatt, right? So for 500 watts per meter square, and also you can see that the current is maintained around 4900, right? So for change in irradiation condition and partial shading effect, right, and the PV power is extracted from the PV panel by means of MPPT, and also the same power will be injected to the grid. Okay, so this is the working of this model.